So I'm chatting with ACES Research Fellow, Dr. Cristina Pozo-Gonzalo from our Deakin University node this morning. Thanks for joining me, Cristina.
Thank you. Thank you for having me, Sam.
It's a pleasure as always. And look, we're chatting this morning about a new paper that was published in Electrochemistry Communications by yourself and a number of other ACES researchers as well as collaborators, researchers at Monash University and then collaborators at the University of Cambridge and Chalmers Technical University, I believe. Could you tell us a little bit more about this paper?
So it has been a long research in this area. So as you know, that one of our main areas of research is on metal air batteries, and we are always looking for electrolytes that they are not volatile, so increase the safety of the battery in general. So one of the families of systems is a phosphonium ionic liquid that has been really good in terms of sodium cycling. So, like maybe I should explain in a metal air battery, and especially the sodium air that we are working, we have on one side, we have sodium metal, and on the other electrode, we have a carbon material. So this is, and in the middle, there is the electrolyte. So this is the composition. So when you choose an electrolyte, you need to make sure that it works for the anode side and from the cathode side. And that's always the challenges. So the phosphonium ionic liquids that we are investigating or we have investigated in this paper, we know that it works really well from the sodium side. So we wanted to investigate what happened on the other side of the battery. So what I said, this is a very complete work, and we have done some modeling, we have done some characterization, but probably what is really interesting in here is that we have studied a new anion for a metal air battery. So this anion is, in terms of battery, is really good because it generated very stable layering on the metal side, but it has been published in the literature that is not very stable from the reduction of oxygen side. It always leads to irreversible processes, so that's what affects the cyclability of the process. So in this case, we saw that by changing some part of this electrolyte, which is in this case is the cation, we were able to cycle or to do the reduction of oxygen in a more stable manner.
Right. And how did this collaboration come together?
So we have, as you say, several authors from different institutions. So we have, on one hand, we have Doug McFarland and Alan Bond from Monash University. So this is part of ACES, the research center. We have a PhD student, which is Laura Garcia Quintana, and one of her supervisors is Alan Bond. So that was why we have Alan in this work. On the other hand, because Doug McFarland is part of ACES and has been one of the leaders in the energy area, he was involved as well from Monash perspective. Then, as you mentioned, there is another author, which is from Chalmers and Cambridge University. So this was a postdoc that he was also part of ACES. He finished his time at the university, Deakin University, and he moved. But we continue the collaboration with him. He's a computational scientist. And then the rest of the team is from Deakin University.
I'm wondering, how does this paper and the research in the paper build on your sort of specific area of work? Because obviously you mentioned there's, a whole range of researchers involved, but, focusing on your specific work, how does it build on that?
So do you know that my background, my area of expertise is mainly electrochemistry, but I have been working on different areas. So, and one of my research lines is also metal air battery. So we have different aspects. So that's where I bring into this team. Then, for example, we have Professor Alan Bond. He's a very well-renowned international electrochemist researcher. So obviously we require also this background, and then all the characterization, the modeling. So we had other different researchers in the team.
So what do you think the future implications for this research are?
So for us, if we want to realize what it will be metal air battery, obviously we require systems, electrolytes, which are stable, they are non-flammable, they are non-volatile. So because keeping in mind that one of the electrodes is a metal, there cannot be evaporation of the electrolyte. It will lead to failure of the battery. So that's for us is that the application. So everything is building up little by little. So we started with very simple systems. We start adding source, increasing the capacity, increasing the cyclability. So we have seen that, especially during this PhD study, we have been improving the properties. So that's, I think, that's in the research area. Obviously, ideally, metal air batteries, it will be really a very good outcomes, because as you know, like we are using oxygen as an active material. There is nothing cheaper and more available than that. So obviously, those are really good implications.
Fantastic. Well, look, thanks for taking the time to explain the paper and the research in a bit more detail with me. It's been a pleasure to catch up. And as you mentioned before we started recording, you guys are going into a week of lockdown. So all the best within the next week.
Thank you. Hopefully it will be only 7 days, so we can come back to enjoy our freedom that we are enjoying in Australia. I think we are very lucky in that regard. So it's all right. Small sacrifice.
Yeah, definitely. All right. Well, thanks for catching up, Cristina.
Thank you, Sam.